All right, I'm going to go a circular motion intro here. I'm not going to really dive into any F equals ma or any of the Newton law type problems. Again, those are the bread and butter physics problems when we start talking about circular motion. I'm just going to kind of stick to the basics of describing some of the things and introduce you to some words that you may not have thought of. So let's just talk about, this is an object, okay? And it's rotating around this thing. We want to talk about all the different things that we can discuss. Okay, so let's just talk about the distance it could go. In Algebra 2, you might have called that the arc length. It's really just the distance traveled. It's literally, how many meters you would go. In an algebra class, like I said, in Algebra 2, you might have drawn something like this. And you would relate r, theta, and I have no idea why, but typically in a math class, they use S for arc length. It's kind of ridiculous. I'm just going to use X. I know X is sometimes a horizontal distance, but X is just going to be an easier variable for us. And so you might have just memorized some formula that said X equals R theta. And again, I want to prove to you where that actually comes from. I hate kind of just throwing out formulas and say, hey, this is the arc length formula. Just memorize this. Let's think this through. And so, do you agree that if I walk around the entire circle versus walking around part of the circle, that it's proportional to the angle I go through? And so if you think and set up a nice, easy proportion and say, well, this distance, x, should be proportional to theta, just like the total distance. Well, if I walk around the total distance, that's just the circumference of the circle, 2 pi r, that should be proportional to the total angle I walk through in a circle, and that's 2 pi. Again, think about this. This is just a proportion, and all this says is, if I walk a certain amount of the circle, it should be proportional to the angle I walk through. And if I walk through the total circle, 2 pi r, it's got to be equal to the total angle I would go through, 2 pi radians, to complete a circle. And if you just get rid of that, you easily get that x equals r times theta. And we get the arc length formula from just looking at the proportion of the arc length is to the angle, just like the total arc length circumference is to the total angle. Okay, so we got this. The beauty of this formula is that now we understand calculus, that we can take a time derivative. So if we look at how these things are functions of time, we can end up with getting some new things. So if we take a derivative of x, we get velocity. R is just a constant, it's not changing. And if we look at, so let's say x, dx dt, we know that's velocity. But we also know d theta dt. Okay, what's theta? Well, theta is so many radians, and that's going to be a new letter for us, and that's going to be omega. So that means that the derivative of theta is omega. So v equals r omega. And this is going to relate velocity to angular velocity. So we have a new word here. This omega, which is a Greek letter, I know it looks like a W, but it's an omega, is what they call angular velocity. And really, it's just how fast you're spinning. It's a spin rate. Think of the units. The units for velocity, well, it's the rate at which you're changing x with respect to time. So it's like meters per second. And this is how fast you're changing your angle with respect to time. So this bad boy is going to be radians per second. It's not how fast you're moving, that's this. It's how fast you're spinning. So you could be spinning around a great big circle, but it's how fast you're spinning, not how fast you're actually moving. Now they're related, well yeah, they're related by this. They're proportional based on the radius. The bigger the radius, the faster you're spinning, of course, the faster you have to be moving. And we can even take another derivative. We take the derivative of velocity, right? What's dv dt? Well, that's acceleration. It's literally the definition of acceleration. And those units are meters per second squared. Well, it just turns out we can look at the rate at which our spin rate is changing. And that's going to be alpha. Alpha, another Greek letter, is angular acceleration. Hopefully, you can kind of see how all these things are going to fit together. Alpha is how fast you're changing your angular velocity, just like acceleration is how fast you're changing your velocity. Again, meters per second squared is meters per second. If you tell me you have an acceleration of like 4, that means you're increasing your velocity by 4 meters per second every second. Well, if you have an angular acceleration, it's going to be in radians per second squared. It's just another time derivative, which means, let's say you had 4 radians per second. It means you're increasing your angular speed, your angular velocity, by 4 radians per second. Again, alpha is to acceleration as omega is to velocity, as angular displacement is to regular displacement. Again, you can be displaced by so many angle measurements that says start here and displace 30 degrees. Go up. Well, that also corresponded to an actual real meter displacement. And again, all of these things are related. So A equals R alpha. Okay, angular velocity, angular acceleration is related to regular acceleration and regular velocity. And again, they might say linear velocity. They might say tangential velocity. Why are they going to say tangential velocity? Well, it turns out when you're moving around in a circle, and let's say we're spinning in this way, if I said, what's the direction of the velocity at that moment in time? Well, we know that it's tangent to the curve. And so good old regular V, linear velocity, tangential velocity are all the same thing as they always have been. It's just V. Now, omega is your spin rate. Okay, in this case, omega would be counterclockwise. And those things are related by the radius of the disk, using this idea. Okay? So we have stuff like that. And then we have even other stuff. And again, this is a little confusing because all of these kind of tell you kind of how fast you're moving or spinning, and sometimes our brain gets them mixed up. But there's another thing called frequency. And frequency means in physics just like it always means in everything else. It's going to be revolutions per second. It's a spin rate. You're like, wait a second, these are both spin rates? And I'm like, well, yeah. This one's going to be in radians per second, and this one's going to be in revolutions per second. And how are they related? Ooh, it's really, really, really easy. If you want to know how many radians you do per second, and you know how many revolutions you do per second, how many radians are there in a revolution? You're like, oh, if I spin all the way around, that's 2 pi. So then omega equals 2 pi f. And you're thinking, oh my goodness, there are so many formulas on this sheet already, and you have to take a breath and think, okay, this is easy. You have to think of the units. This is how many times you spin around in a second. Let's say you had a frequency of 3, okay? 3 hertz. Hertz is some silly unit that we give credit to some scientists. Hertz is just revolutions per second. 3 hertz, 3 revolutions per second. That means you go around this thing 3 times in a second. Well, every time you go around, it's 2 pi radians. So how many radians are you doing? Well, it's just 2 pi times 3. So you do 6 pi radians per second is equivalent to a frequency of 3 hertz. So this formula is fairly obvious. Okay? How about another one? How about period? Period is a capital T. Don't confuse it with tension. The period is the time it takes to do 1 revolution or 1 cycle. Well, how is that related? Well, that's just the inverse of frequency. That's not too bad. The inverse of frequency. Frequency is revolutions per second. Well, what's period? It's seconds per 1 revolution. So those have to be inverses of each other. Or maybe I shouldn't say inverse. They're reciprocals of each other. Meaning, if you have a frequency of 2 hertz, okay, that means you can do 2 revolutions in 1 second. Well, how long does it take you to do 1 revolution? Well, half of a second. Considering you can do 2 in 1 second, that means you have a period of a half of a second. See how easy that relationship is? And so you have this crazy loop of you can know period with frequency, frequency with angular velocity, which is just spin rate, but so is frequency. It's just a different type of spin rate. One's in radians per second, one's in revolutions per second. But then you can relate velocity to omega. And so all of these things, all end up being connected. You can try to write as many formulas as you want, but I would just kind of know the standard ones. For me, these three are absolutes, right? In calculus, a little geometry, and then calculus does the rest. That one just makes logical sense to me. This spin rate is related to this spin rate, and they're just off by revolutions and radians. And then this relationship between period and frequency makes a lot of sense. And then all of a sudden, you have this domino connection between the rest of them. Okay, the last thing I want to kind of introduce in this circular motion idea is centripetal acceleration. We haven't gotten to it yet, but let's be clear. If you're moving in a circle, you're being forced to move in a circle. You just don't move in a circle just because you want to. Something forces you. Friction, tension, a normal force, gravity, some force, some inward force is changing your direction. If you don't have a force acting on you, you know how you move? You move in a straight line. And you would keep moving in a straight line until something messes with you. Right? That's Newton's first law. An object tends to stay in motion unless it's acted on by some outside force. Okay, so if nothing messes with you, you move in a straight line. If you want to bend this way, there has to be an inward force. And so if we look back at our circular motion, we've decided that the angular, if we're spinning this way, the angular velocity we would say is counterclockwise. The velocity at the top would actually be tangent. In this case, it would be left. But where's the acceleration? And again, if you're moving this way and you're spinning in this direction, if you're here, the force is inward. Always, always inward. There has to be some sort of inward force. And then that force produces some centripetal acceleration. And what we also know is this is a key relationship. You're going to use it almost every problem. Is that we know that the centripetal acceleration is equal to v squared over r. And again, you can put a big old box around that, and you're going to do that about 1,000 times this unit. That's a nice relationship that we know, and now we have a connection between almost every single variable that's involved in circular motion, right? Linear distance, or just distance, that's in meters. Meters per second squared. That's good old position, velocity, and acceleration. And now we have the angular equivalent. We have angular displacement, angular velocity, and angular acceleration. Radians, radians per second squared. Well, we have a different type of spin rate. We have omega, right, angular velocity in radians per second, and then we have frequency, which is still a spin rate. It's just in revolutions per second. I know you've heard of like RPMs. RPMs. You've heard of a car and the number of RPMs it's going. Revolutions per minute. It's a type of frequency. It's not the standard units because it's not in seconds. It's in minutes, but it's still in revolutions per minute. It's giving you a spin rate. Okay? We have period, which is the time it takes to go around, which is the reciprocal of frequency. This is revolutions per second. This is seconds per one revolution. And then we connect all of those things to centripetal acceleration. And I guess I also want to make a note. If we know that v is omega r, then we can also say that centripetal acceleration is also equal to omega squared r. And it's going to turn out that every now and then that's going to be more useful because we're more interested in relating the centripetal acceleration to omega than we are to velocity. Again, probably 8 or 9 times out of 10 we're going to use this one, but there are going to be times where we're super interested in the spin rate, not the actual rate at which we're moving in meters per second. Okay? Hopefully this gave you a kind of an introduction to a whole bunch of new letters and relationships. Try not to memorize these formulas. It's way easier to understand the concepts. And again, I'm going to argue that if you think of the units, it will tell you the relationship. If you think of the units for omega, radians per second, you'll figure out that omega has to equal 2 pi f. because this is revolutions per second. Well, how are you going to go from revolutions per second to radians per second? I don't know, multiply by how many radians there are in a revolution. So these things are going to make sense after a while, but after a week or so of doing more problems, you'll get the hang of it.